All right, so this video is for section 4, chapter 4, geometry. We're going to talk about isosceles triangles. So some theorems and corollaries to go with those. Otherwise, an isosceles triangle is a triangle with at least two congruent sides. Remember that. Otherwise, there's some labels that are going to go in this picture that you definitely need for your notes. We need to know that this top angle, these are the sides that are congruent to each other. That top angle is going to be called a vertex angle. These two sides are called legs, the congruent sides. Otherwise, your base is down here, and these two angles down here are my base angles. And that's where our first theorem comes into play. If you have an isosceles triangle, right? So this is the isosceles triangle theorem. Short for that, we say ITT. So it's kind of like CPCT. You can just write that in your proof, and I know what you're talking about. But this is the isosceles triangle theorem. So you can write that shorthand there. But if two sides of a triangle, hold on here, are congruent, then the angles opposite those sides are congruent. Sorry about the handwriting today. It's even worse than normal. But those two base angles, they are always congruent in an isosceles triangle. That's all we're trying to say. If you know it's isosceles, you know those base angles are congruent. That's going to be ITT for short, isosceles triangle theorem. Otherwise, there's lots of corollaries to go with. Some of these we've actually talked about before, right? If a triangle is equilateral, then it should also be equiangular. Right, so we already kind of figured that out in the past. But if it's equilateral, then all of the angles are 60 degrees. Again, something we've talked about before. But then this one's new. The bisector of the vertex angle of an isosceles triangle is perpendicular. Hold on a second. Perpendicular to the base at its midpoint. So that's going to be kind of useful to know if you do have a bisector of that vertex angle. It's going to be perpendicular to the base of the midpoint. That's going to come into play later when we talk about altitudes, when we talk about medians. This is technically both an altitude and a median in this case, right? But that's something that could be useful. It could shorten one proof later. Otherwise, you're not going to use it a lot. It's just something that we could definitely know. And then our second theorem, this one's a little bit tougher to recognize than the other one, but it's the same thing technically. So this is our converse of isosceles triangle theorem, so ITT. So to shorten it, we're going to call it CITT, right? But if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So this is how we could prove, if we knew two angles were congruent in a triangle, that it's definitely an isosceles triangle. So this is definitely going to be useful. So it's the opposite, because before we knew the sides were the same, so the angles should be the same. Otherwise now it's the angles are the same, so the sides should be congruent. The corollary to that we need to write in is if a triangle is equilateral, a triangle is equiangular, then it is equilateral. Again, something technically we were already working off of, but now we have the theorems that it's connected to. So when we look at these examples, if I'm trying to solve for x, and I know this is an isosceles triangle, I know actually both of these angles are congruent in an isosceles triangle. That's my ITT theorem. Then I know that 2x's plus 30 would be 180. So I can solve for x, right? X should be 75 when I do the algebra there. Otherwise, when I'm looking at this next picture off to the right, I know that these two sides opposite my angles are going to be congruent. So that means 2x minus 4 equals x plus 5. And I can solve for x again. I don't even need this information, the 2x plus 2. I'm not really going to use it. Although I could figure out what it is later once I know what x is. But again, solve here and you get x equals 9. So those two sides are congruent because 18 minus 4 is 14. So this side is a 14. 9 plus 5 is 14. This one over here is not congruent, so 18 plus 2 is actually 20, right? We know that that's not congruent to 14 or 14, but we could have found out what it was. Depends on what you're asked for. So then the next one, same idea. I just need to know that these two angles opposite of these congruent sides are congruent. So I know that I have two 55s, which would be 110 plus x equals 180. So x is obviously a 70, right? This one over here, again, I don't know yet, but I'm assuming 62 plus 56 is 108. So this other angle over here is probably going to have to be a 62 to make 180 total. So now that I know that these two angles are congruent, I know that these two sides would be congruent. So x is obviously 42. And we keep going from there. So we got a proof here. So I got to prove that angle 1 and 2 are congruent. Or excuse me, I'm given that angle 1 and 2 are congruent. I have to prove that OK is congruent to OJ. So my given angle 1 is congruent to angle 2. First thing I'm probably going to do is my vertical angles. Angle 1 equals angle 3. Angle 2 equals angle 4. So vertical angles are congruent. Then I'll do a substitution, probably, because I want to know that angle 3 is congruent to angle 4. Because now that I know that these two angles are congruent, this could also be transitive, by the way. Now that I know that 3 and 4 are congruent, I can use my CITT to say that OK is congruent to OJ. Again, one of the biggest things is recognizing which thing you did. If I know the angles first, and that's how I proved that the sides are congruent, that's a CITT. If I knew that the sides were congruent, and that made the angles the same, that's when it's CITT. So this is technically my converse isosceles triangle theorem. Otherwise, you get the gist of it.